No questions, so we will start right away. So looking at sets, then we did polynomials, then we did factorization. We also looked at linear equations in one unknown variable. And later on, we will look at quadratic equations. But first, we need to look at these objects called complex numbers. These are mathematical objects called complex numbers. So over this week, we will be discussing complex numbers, and I'd like us to focus on the following. We will introduce numbers, complex numbers, then we will perform algebraic operations. Algebraic operations. In this case, I'm simply referring to addition, multiplication, subtraction, and division of these objects, just as the way we do with real numbers. Then we will look at representation. So the same way we can represent real numbers on a real number line, we will see the equivalent for complex numbers. Then we will see how to find powers and roots of complex numbers. So essentially, my aim is that by the end of the week, all of you should have known what's a complex number. Then we should be knowing how to deal with them. How can you add them? How do you multiply them? How do you divide them? How can we represent complex numbers in a graph? And then how can we find powers and roots of complex numbers, just as the way we do real numbers, okay? So first things first. In your previous level of education, you dealt with equations, solving equations. And in fact, in the class, we learned to solve equations of the form ax plus b is 0. This is a linear equation in the non-variable x, because x here has power 1. And we saw how to solve this, that in general, you'll find x is negative b divided by a, because as long as a is not 0. And I also hinted at the idea that not all equations that we deal with in mathematics have solutions. For example, suppose you wanted to solve the equation x squared is equal to 4. Well, from the topic indices and exponents, you know that this is a number which, if you multiply by itself, gives you 4. And this is the same. If you want to solve this, one of the ways is to find square root of both sides, okay? So square root of x squared will be x, square root of 4 will be plus or minus 2. So you find that a real number plus or minus 2 will satisfy this equation. The 0 of this equation, or it's a root of this equation. But there are some equations. For example, x squared plus 1 is equal to 0. So let me call this equation 1. Equation 1 has a real root. In fact, it has 2 real roots. I'll be telling you about fundamental theorem of algebra in either today's class or the next class, that will tell you the number of roots to expect, or the number of solutions to expect to any equation of any degree. For example, this is an equation of degree 2. And by the fundamental theorem of algebra, we expect at most 2 roots. And you find that there are only 2 roots, positive 2 and negative 2. Those are the only real numbers for which this equation will be true. If you try solving an equation like this, x squared plus 1 is equal to 0, following the same approach or via the same analogy, then you will first of all subtract negative 1 from both sides, or add negative 1 to both sides, so that from this equation 2, you have that x squared is equal to negative 1. When you are looking at the real number line as a vector space, I told you that every real number, if you take the square of any real number, be it positive or negative, you will always get a positive number. So we know that for all x in the real line, x squared must be greater or equal to 0. In other words, if you take any real number, then a real number squared will always lie on the interval from 0 all the way to plus infinity. For example, if you take -3 is a negative number, squared gives you 9, which is a positive number. If you take 5, squared gives you 25, which is a positive number. So this is a fact which we know. Any real number squared must always give you a positive number. But trying to solve this equation 2, we realize that x squared is -1. Well, x is a real number. So it's not possible to have the square of a real number being a negative, because -1 is less than 0. This does not satisfy this condition. So it means the set of the real line is not sufficient for our applications or for doing mathematics for its own sakes. So, for example, you cannot find the solution of this equation in the real line. So if someone asks you to find the solution of this equation in the real line, then the solution of this is the empty set. There is no real number which can satisfy the equation x squared is -1. This calls for introduction of a new system of numbers which will accommodate equations such as x squared is equal to -1. So because of this, we will define a new number. Define a number denoted by I, which is the square root of -1. So from here, if you find square root on both sides, you'll have that x is the square root of -1. It is this square root of -1 which we are going to denote by I standing for imaginary. And then from this, it means that I squared is equal to -1. I've just squared on both sides. So squaring on this side, I get I squared. On the right hand side, squaring will remove the square root symbol because the power and the root cancel out and I get what is under the root, which is -1. Now, once we have defined a new number, I, whose square is -1, then that means we can find square roots of all real numbers, positive or negative. So with this, we can define a complex number. Complex number is a number of the form a plus ib, a plus bi, a plus bi, because multiplication is commutative. It does not matter whether you start with I times b or b times I. Where a and b are real numbers.
Sure, the board can't be seen. Your handwriting is not visible.
My handwriting is too small.
It's not visible.
No, listen. Is it my handwriting that is small or there's too much light?
There's too much light.
Okay, let me try again. Then I use a different pen. So definition. How about now?
It's better.
Still bad.
No, it's better.
Okay, good. So we've just defined with this, just defined a complex number as is a number of the form a plus bi, where a and b are real numbers. A and b are real numbers. And there's this condition that I squared is equal to -1. I hope by now all of you are familiar with real numbers. You all know what a real number is. So any number which can be written in the form a plus bi, where a and b are real numbers, I has the property that if you square it, you get the real number -1. We call that such a number a complex number. Let me give examples of complex numbers. Examples. For example, number like 2 plus 4i. This is a complex number. 2 and 4 are real numbers. So 2 plus 4 is a complex number. And before I give another example, you will notice that if you have the number a plus bi, okay, let me call this number z, then it has two parts. There's a real part and there's an imaginary part. The real part is the part without I, and the imaginary part is the part which is the coefficient of I. So we say that the real part of z is a, and then the imaginary part of z is b. And I've said the imaginary part is simply the part which is the coefficient of I, and the real part is the part which is not the coefficient of I. So for example, the real part of this complex number 2 plus 4i is 2, and the imaginary part of this complex number 2 plus 4i is 4. Okay? Now, there are so many ways you can have complex numbers. You could have some complex numbers for which a is 0. When a is 0, you will have the number z is bi, because it's 0 plus bi, and we know 0 is an additive identity. So any number you add to 0, you do not change that number. So bi, such a number is called pure imaginary. So complex numbers of the form, let me just write complex numbers for which the real part is 0 are called pure imaginary numbers. They are called pure imaginary numbers. Okay, so example of a pure imaginary number is a number like pi times I, or 3 times I, 10 times I. These are examples of pure imaginary numbers because they do not have the real part. The real part is 0. You could also have complex numbers for which the imaginary part is 0. That's going to be a very special case when the imaginary part of z is 0. We have that z is a. So it should be a plus 0i, but because the imaginary part is 0, we just have a. Now on this, note that all real numbers are complex numbers, for which the imaginary part is 0. So think about any real number. It's a complex number, only that the imaginary part is 0. So for example, numbers like e, pi, 2, 20,000, all these are complex numbers. They are real numbers, but the complex numbers for which the imaginary part is 0. So what I'm trying to say is that the set of the real line is a subset of the set of complex numbers. We use this C to denote the set of complex numbers, where the set of complex numbers contains numbers of the form a plus ib, such that A and B are real numbers. This is the definition we just gave before. So the set C for which the numbers can be expressed in the form A plus IB, where A and B are real numbers. This is a set of complex numbers. And all real numbers are subset of complex numbers, which means all real numbers are actually complex numbers for which the imaginary part is 0. Any question up to this point? Any question up to this point?
So I have a question.
Good. Go ahead.
So I wanted to ask the kind of question can be asked in an exam.
In an exam?
Yeah.
Yes, I could ask you to define a complex number and give an example of a complex number. I could ask you to add two complex numbers, multiply complex numbers, divide complex numbers, subtract complex numbers. But we are about to see how we do that.
So
Okay.
this is the equation A plus PI. The PI is imaginary part, so it means the PI is equal to 0, Amma.
No. BI is not imaginary part. It is B that is the imaginary part, B. We say the imaginary part is the coefficient of the I. So the real part of this number is A, the part without I. The imaginary part is B, the part that is the coefficient of I. So
Yeah,
for a real number, B is 0. So you just have A. So it's like you have A plus 0I, but you know 0 is an identity. Add 0 to anything, you do not change that object. So it's like a real number is simply a special complex number with the imaginary part 0. And that's why we say the real number, all real numbers are subset of complex numbers. Okay. And
So I have a
Yeah.
question.
we also have pure imaginary numbers for which the real part is 0. Go
I have
ahead.
a question.
Go ahead.
This imaginary number, are we ever going to find the value or what's its purpose?
Oh, good. So you're asking why we are studying complex numbers? Why we are? Is that, did I get it right? Are you asking why we are studying complex numbers?
Yes, basically why we're using imaginary numbers in mathematics.
Good. That's a good question. That's a very good question. So let me give you some applications of complex numbers in real life. There are so many applications of complex numbers in real life. I will not discuss all of them. I'm just going to give you a few. Applications of complex numbers. And I'm afraid some of these applications will involve some other higher order mathematics, which some of you, most of you have not encountered before. So I will not go deep, but I'll just explain what's involved. The first one is signal processing. Signal processing. And to be precise, this is done in Fourier analysis. Which is simply the study of how to represent signals using their frequencies. For example, how is it that I'm able to talk here at USIU and you guys, wherever you are, some in Liberia, some in other parts of Kenya, be able to get me at this in real time, okay? This is only possible through signal processing. So what this platform does, Zoom, they simply take the coordinates of this place and that is what they send to you so that you are able to interact with me in real time, okay? For the analysis, you take a signal, for example, it could be a sound wave, okay? And then you simply try to identify which frequencies are important in this signal. So if you want to transmit this signal, you don't have to transmit all the frequencies because you're trying to conserve space for your machine. And also you are also interested in the time it will take for you to transmit signal from one place to another. So just do a Fourier transform and then transmit only the important parts of your signal. Then on the receiving end, you can also do an inverse Fourier transform and get your original sample. For example, those of you who follow what happens in space, NASA, some few months ago in February, they landed a space vehicle in Mars, and they were able to record some sound from Mars. But this sound came with noise. There was some interference because of what happens in space. But through Fourier analysis or Fourier transform, they were able to remove the noise and get the exact sound from Mars. So that's how powerful complex numbers can be when you apply it to signal processing. Other applications could be in electricity. And by the way, engineers do not use the symbol I. We are saying I is the square root of -1. If you read most engineering texts, you will find that they refer to this as J. So engineering texts, they use J as the imaginary number, the square root of -1. And in electricity, they use this to understand what happens in electric circuits. If you want to study the impedance or resistance when transmitting alternating current, or AC, you do this via complex numbers, and these complex numbers are also applied in other fields like quantum mechanics. Maybe some of you have heard of Schrodinger equation, where you are trying to study the space of subatomic particles like neutrons and photons. You need a Schrodinger equation. There's some element of probability, so you also need to understand some probability for you to do this quantum mechanics. But this is related to in fact, the Schrodinger equation itself has the complex as this imaginary number. Then there is also another application, actually quite a number of them, dynamical systems. So this is a system which is constantly changing over time, and related to that, we have vibrational analysis. An example of dynamical system would be studying the dynamics of a disease. For example, coronavirus. How does it spread? Okay. How is it transmitted from one person to one person? What is the impact over some period of time? There is also an application in fluid mechanics or fluid dynamics. And this is very important because without fluid mechanics, you cannot drive cars. Without fluid mechanics, planes cannot fly. Without fluid mechanics, we cannot have ships in the ocean. Without fluid mechanics, we cannot be able to study how drug is effectively transmitted in your body. Okay, so this is how we use, especially in fluid dynamics or mechanics, we use to understand what we call potential theory. Well, for some of these applications, actually most of these applications, you will need more mathematics concepts like functional analysis. You will need complex analysis. So where you're doing analysis on the complex plane, I will tell you in a few minutes what's the complex plane. Okay, so these are some few applications of complex numbers that we have in real life, but there are some more applications of complex numbers. So you don't just study complex numbers for the sake of it. They have real life applications. Is that better? Did I answer your question? The person who asked why we are studying imaginary numbers, or what's the use of studying?
Yeah, somewhat, sir, somewhat. It's okay.
Somewhat. Which part? I want to. Which part is it? Which part did I not answer successfully?
Okay, no. Like when I asked, I wasn't really looking for applications. I was wondering if the I really has a value, or it's because I'm going through the notes and every answer and every solution, the I is just an I. So I'm wondering why we're learning about an image.
I has a value. I is the square root of -1.
Okay.
The real number -1. Huh?
Okay.
Its square root is called I. It has a value. I is the square root of -1.
Okay. Then why is it imaginary? But I'll understand some more.
It's imaginary because it is not a real number.
Okay.
Remember when we were studying real numbers and there are subsets like integers, natural numbers, rationals. So a real number is a number which is either rational or irrational. Remember, if you take the union of rationals with irrationals, you get the real line. So all elements of the real line are real numbers. Okay. And by a property of the real numbers, we know that if you square any real number, take any real number and multiply it by itself, you'll always get a positive number. For example, -4 squared is 16. -10,000 squared is some very big positive number. If you take something like 2 squared is a positive number. So any real number squared will always give you a positive number. Complex numbers come in when you want to deal with equations like x squared is -1. Because we know for any real number, if you square, you must always get a number which is positive, greater or equal to 0. But here is a case where you're getting -1, which is strictly less than 0. So no real number will have this kind of property. Therefore, to deal with such equations and any other equations which end up to this situation, we must define a bigger system of numbers. Remember how we developed the real line? We started with natural numbers, counting numbers. We start counting from 0 when there is nothing, 1 when there's one object, 2, 3, 4, like that, up to infinity. Then we tried to solve some equations and realized there are some equations whose solutions will not be natural numbers. So we need negative numbers, or the negatives of the natural numbers plus the natural numbers. That gave us integers. Then we tried to solve some equations and realized that even the set of integers is not enough. We need fractions. Then we introduced rational numbers. And in some cases, we also need irrational numbers, numbers which cannot be expressed as fractions, numbers such as pi, e, square roots of all prime numbers. Those are irrational numbers. So when you take the union of rational numbers, you get the real line. And then this is still not enough. So we define a larger system of numbers called complex numbers. And let me hint to you, but we're not going to go to that extent. There is even a bigger system of numbers, a bigger system, bigger than the complex numbers. They're called quaternions, which have, these complex numbers have just one imaginary part. We said they have a real part and an imaginary part. We have bigger system that has 3 imaginary numbers, the quaternions. They exist in 4 dimensions. This exists in 2 dimensions. I'll explain to you what I mean by 2 dimensions. And after quaternions, we also have a bigger system, octonions, which will now have 7 imaginary numbers, but we will not go to that extent. We will just talk about complex numbers. So I want you guys to have a very solid background of understanding of what is a complex numbers. Shall we continue, or do we have more questions? Hello?
You can continue.
Yes.
You can continue, sir. Give us an example. Do give us something. Something.
Okay, let's continue. So after defining complex numbers, of course, given you examples, if you want more examples, you will have -2 plus maybe I is a complex number. So let me write a complex number and you guys will tell me the real part and the imaginary part. Let me have also 22/7 plus 8I. Let me have 0. Let me have 1. Let me have 22 minus 67I. Okay, so let's go quick. This complex number, -2 plus I, what is the real part?
-2.
And what's the imaginary part?
1.
The imaginary part is 1, not I. So the imaginary part is the coefficient I. Some people will make a mistake and say the imaginary part is I. How about this second one?
22/7 real part.
2/7 is the real part, and the imaginary part is 8.
8.
How about this guy?
Real part 0, imaginary part 0.
Good. Real part 0, imaginary part 0. How about 1?
Real part 1, imaginary part 0.
I want to have a different voice. It's like it's only some few people talking. Complex
The
number.
real part is 1, and the
Real
part
imaginary
is one.
part is 0.
Yes, the imaginary part is 0. And lastly,
22
Real
real
part is
part.
22.
22.
Imaginary is 67.
really,
Minus 67.
the imaginary part is minus 67. Good. So let's do, so at least you know some few examples of complex number. It's very easy to get a complex number. Think of any real number, any two real numbers, and make first part to be the real part, another part to be the imaginary part. And remember, the imaginary part is simply the coefficient of I. Now let's do algebraic operations. Algebraic operations. So now that we have defined these objects called complex numbers, what do we do with them? Can we add them? Can we subtract them? Can we multiply them? Can we divide them? If so, how? First, addition. To add complex numbers, add two complex numbers. Add real parts and add imaginary parts. Okay. For example, let's say I have a complex number Z1 is A1 plus B1I, and another complex number Z2, which is A2 plus IB2. Then adding this, so Z1 plus Z2, I've said add the real parts and add the imaginary parts. The real part of Z1 is just A1. The real part of Z2 is just A2. So the sum of these two complex numbers will be A1 plus A2 added to the imaginary parts, also add them separately. So the imaginary part of Z1 is B1, imaginary part of Z2 is B2. B1 plus B2. Let me give you a concrete example. Add the following. Add the following numbers. Add the following numbers. So let's say we have 3 plus 4i, a complex number, plus 2 minus 6i. So we have two complex numbers. The first one is 3 plus 4i, the second is 2 minus 6i. And the rule is that add the real parts and add the imaginary parts. So this will give us the real part of the first one is 3, the real part of the second is 2. So the real part of our sum will be 3 plus 2 plus imaginary part. We also add the imaginary parts. Imaginary part of the first is 4, imaginary part of the second is -6. So plus 4 plus 6. And what does this give you? 5 minus 2i. So the sum of these two complex numbers is the complex number 5 minus 2i. Very easy. How about the complex numbers a plus 2i plus 2 minus xi? What will be the sum of these two complex numbers? Hello? Remember here, I could also ask you, instead of saying add, I would just say express in the form a plus ib. So first thing, identify the real part of the first number. The real part of this is A. The real part of this is 2. So add them, you get A plus 2 plus imaginary part of the first is 2. Imaginary part of the second is negative x. So plus 2 minus I. So the sum of this is A plus 2 minus x I. Good. How about division or subtraction? Subtraction and division are analogous. The same way we add is the same way we subtract. So just the way we add imaginary parts together and we add the real parts together, when doing subtraction, take the real parts, subtract them, and take the imaginary parts, subtract them, and then you have your resulting complex number. Subtraction. The rule is subtract real parts and subtract imaginary parts. For example, if you have Z1 as A1 plus I B1 and Z2 as A2 plus I B2, then Z1 minus Z2, I check the real part of the first and the real part of the second and subtract them. So that gives me A1 minus A2 plus, check the real part of the first, B1 minus B2. Example, let me take the same numbers, but then just change the operation. So take 3 plus 4i minus 2 minus 6i. And I also want to take a plus 2i minus 2 minus xi. Start with the real parts. So the real part of the first number is 3 minus the real part of the second number is 2. Add these two. Real part of the first is 4. Okay. Subtract the real part of the second. So it's minus 6. There's a minus outside and a minus inside, so it's minus. And this gives me 3 minus 2 is 1 plus 4 minus 6 is like 4 plus 6. So that gives you 10i. Here, the real part is A. The real part of the second part is 2, so A minus 2 plus the real part of the first number is 2. We are subtracting the real part, the imaginary part of the second number, so minus x. And this gives.
Why is there a plus in between the brackets?
Where?
In the middle of the brackets. Why is there a plus?
Yes, there's a plus because I'm adding the real part to the imaginary part. That's why I put the plus here. So remember the rule of subtraction is subtract the real parts together, subtract the imaginary parts together, then add the results. Add the result of the real part with the result of the imaginary part. And remember to put I after the imaginary part. So what I did here is I took 3 minus 2, I got 1. Then I took 4 minus 6, gave me 10. So 10 is the imaginary part. So therefore my complex number is 1 plus 10i. Okay? Similarly here, I take A as the real part of the first number, subtract 2 real part of the second number, I get A minus 2. And then, so A minus 2 is my real part of the new number. And then I take 2 imaginary part, subtract negative x. So that gives you, we'll have A minus 2 plus I times 2 plus x. So whether it is addition or subtraction, add or subtract the real parts, add or subtract imaginary parts, and then put them together. Remember, a complex number consists of a real part and an imaginary part. So to get the sum or a difference, find the sum of the real parts or the difference of the real parts, find the sum of the imaginary part or the difference of the imaginary part, and then what you get, put together as a complex number. Any questions?
I have a question.
Yes, go ahead.
Right there on the last example, you said that your answer is the last bracket is 2 plus x.
Yes.
Why isn't it 2 minus x?
Why is indeed 2 minus x?
Yes.
Good question. What is the imaginary part of this number?
It's 2i.
Imaginary part is 2.
Oh, sorry, 2. Sorry.
Imaginary part is 2. We are subtracting, okay?
Yes.
What is the imaginary part of the second number?
X.
Are you sure it is x?
Yes.
Really?
It's
It's minus x, not x.
minus x. Okay. Mhm.
You are subtracting from 2, you are subtracting minus x.
Okay.
Minus
Gives you a positive.
that's why we have 2 plus x here.
Thank you.
Good. Any more?
So I have a question.
Yes.
There you said when you put them together, you add plus I, isn't it?
Sorry?
When you're adding or subtracting, you put plus I.
Yes, yes.
So what if you put minus I?
If you put minus I, that is something else, but not addition or subtraction.
Okay.
For addition and subtraction, the rule is simple. Identify the real part and the imaginary part, and I've shown you how to do that. If you're adding 2 numbers or subtracting 2 numbers, your job is to identify which is the real part, which is the imaginary parts, add or subtract the imaginary parts wherever they are, add or subtract the imaginary parts wherever they are, and then combine the 2 to get your resultant complex number. More questions? Good. Let's look at multiplication. Multiplication of complex numbers. Multiplication. Very easy. Now, to multiply 2 complex numbers, so multiplication is a bit different. We are going to multiply 2 complex numbers the same way we deal with numbers like A plus B, C. The same way we do this, but then we have to keep in mind that there's a rule that I squared gives you -1. Okay? We're going to deal with multiplication of complex numbers as we have dealt with surds like this, what we did in the last class, combining surds. But the only rule to keep in mind is that I squared is -1. Let me show you how we go about this. Suppose you have 2 complex numbers. Let's say Z1 is A plus IB, and Z2 is C plus ID. Then to multiply these 2 complex numbers, so I want Z1 times Z2. So this will be A plus IB in bracket multiplied by C plus ID. Are you together? Are you together up to this point?
Yes.
Good. Now we are going to do expansion. Remember expansion of terms? So I need to check all the terms in the left bracket.
I'm not understood.
Right bracket. Someone talking?
I'm asking if you could repeat. I'm not understood.
Okay. So
And could you state the rule?
sorry?
You see like how for addition and subtraction you stated the rule before the examples.
Yes. But for the rule for multiplication, I want to show you how we get to the rule. Huh? I haven't stated the rule first.
Okay.
Because the multiplication is a bit different. So I've not stated the rule yet. We are about to get the rule for multiplication of complex numbers. We didn't state the rule yet. The only hint I gave is that to multiply complex numbers, treat them as surds, the way you multiply surds, or the way you will expand some binomials or trinomials, okay? So suppose you're given two complex numbers, Z1, which is A plus IB, and Z2, C plus ID. So the real part of this is A, imaginary part is B, the real part of this is C, imaginary part is D. Then we want to multiply these two numbers. So the first number is Z1, second number is Z2. I'm multiplying Z1 by Z2. Now, at this point, what I need to do is to expand this expression. Expand. Take every element of the first bracket and use it to multiply all the elements of the second bracket and then combine. So first, I will have the first number A multiplied by C plus ID plus the second part is IB multiplied by C plus ID. I'm just doing normal expansion, taking all the terms of the first bracket, multiplying by all the terms of the second bracket. This is the reverse of what we call factorization. And we did this before when we're dealing with surds. Now what you need to do is open the brackets. So the first bracket, A times C, that is just AC. A times ID, so plus AD times I. I've opened the first bracket. I've taken A multiplied by C, then A multiplied by ID. So I have ADI. Remember, multiplication is associative and it's also commutative. So this, whether you put I times AD or AID or ADI, it is the same thing. There is no problem. Now, second, we have IB times C, that is BCI, plus, now I have IB times ID. So first, I times I is I squared. Then B times D is BD. Okay? So what we have here is AC plus, so remember I can factor out I from this because there's I in this second term and I in this third term. And I have AD plus BC multiplied by I. Then over here, there is a rule I wrote somewhere that I squared is -1. So treat I is the square root of -1. So if you take the square root of something and square it, you get what is inside the bracket. So what we have here is that this I squared is -1. So -1 times BD becomes minus BD. So the real part of this product, so from this we have that Z1 multiplied by Z2 is going to be AD minus BC plus I times what we have here, AD plus BC. This is the rule that we're going to use for multiplication of complex numbers. You start off with writing each complex number into real and imaginary parts like this in this bracket, and then you do the reverse of factorization. Expand. Take every term of this first bracket, multiply by all the terms of the second bracket. Okay? So you can write that as
Sir,
you can state. Yes?
like where you put Z1 times Z2, isn't it like AC minus BD instead of AD minus BC?
You're asking where is?
Like there in the other board, you put like AD minus BC, isn't it AC minus BD instead?
Oh, sorry about that. It's AC minus BD. Sorry for that. I made a mistake. It's AC minus BD as we have here. I hope every other thing is okay.
I have a question. Why does the I keep switching sides?
Why does?
The I keep switching.
Which I?
You see, like, on the left, not the last one, but the one on top, it's AC plus ADI plus BCI. But how comes on this other one, it starts with the I squared is equals to BD? I squared BD, sorry. The one that you're pointing.
Here,
No, the one on top.
this one,
No.
this one.
The one that, okay, yeah, that can work as well.
Uh-huh.
The one on top of it, it says AC, the one that you've underlined,
Uh-huh.
AC plus ADI plus BCI plus I squared BD.
Yes.
Why is it in the ADI comes after, and in this other one, the I comes before?
Where? Here.
No.
Oh,
you see,
okay. I get what you mean.
yeah.
You want us to write this as BD multiplied by I squared.
Yeah, so does the position matter?
Yes, it's okay. It's okay. It doesn't really matter because multiplication is commutative. You know, 2 times 4 is the same as 4 times 2. So whether I write IB or BI, there is no problem.
Okay.
Yes. So now here you just need to remember that I squared is -1 because we defined I as square root of -1. So this term BD times I squared is like BD times -1. Then over here, what I've done is to simply combine what we have on the real part, all the parts that do not involve I, and they are AC and minus BD. So I have AC and minus BD with the real part of my product. And then the parts that contain I will be my imaginary parts. So I just took AD plus BC and put them over there. So let's look at a concrete example. So we usually asked to express in the form A plus IB. Let's say you have, let's look at a simple example, 1 plus I times 1 minus I. So maybe we need to do 2 examples. So that's A, B, maybe 2 plus 4I multiplied by 6I. Yes, and maybe C, 2 multiplied by 4 plus 7I. Let's look at these 3 examples quickly. The multiplication. Now, the way I like to treat multiplication of complex numbers is not to cram this formula, because if you try to cram this, it will confuse you. Just develop this from, just understand the process. How do you expand? The only prior knowledge you need to have is how to expand a factored form of an expression. How to take elements of the first bracket, multiply all elements of the second bracket, and then to combine them. The only rule I need you to remember is that I squared is -1. This is the only thing you need to remember for you to do multiplication. First part, we want to do 1 plus I by 1 minus I. So what you do, take all elements of the first bracket, multiply by all elements of the second bracket. So we start with 1, this one, we multiply by the second bracket, 1 minus I, plus, here we have I multiplied by 1 minus I. So this is going to be equal to 1 times 1 is 1. 1 times -I is simply -I, plus I times 1 is simply I, then I times minus I. So we have here minus I squared. So the minus is this one, and then I squared because I'm taking I times I. So what does this give us? We have 1. There's a minus I plus I. What's minus I plus I?
They cancel out.
0.
Right? 0 plus, let me do minus, and then what's I squared?
-1.
-1.
1. So minus 1. And this gives you 1, then minus
Positive.
positive. So that simply gives you 2. So this complex number multiplied by that complex number gives you 2. Okay, we're getting a real number. The imaginary part is 0 because the I is cancelled out. Any question on this example? And this is a very special example which I'm going to keep. So, second example is 2 plus 4i multiplied by 6i. B, now 2 plus 4i multiplied by 6i. What you do is take all elements of the first bracket, multiply by everything that's outside. So I will take 2 multiplied by 6i plus 4i multiplied by 6i. What is 2 times 6? That's 12. So this is 12i plus 4 times 6, that gives you 24. I times I, that gives you I squared. Okay. So this gives you 12i. Then you know that I squared is -1. So that is going to be minus 24. Therefore, the number, the final answer is -24 plus 12i. There's no problem if you write it like this, but for consistency, just start with the real part followed by the imaginary part for consistency. But there is no problem if you leave the answer in this one. And then lastly, this one you don't even need to do this. What is the answer for this part C?
8 plus 14i.
What?
8 plus 14i.
Good, 8 plus 14i. 2 times 4 is 8, 2 times 7 is 14. Any question on multiplication of complex numbers? I've told you that the trick is learn how to, or just remind yourself, because it's something we did, how to expand an expression, a product of elements into brackets. You must take all elements of the first bracket, multiply by all elements of the second bracket. And the direction doesn't really matter. You could also start with the elements of the second bracket, multiply the elements of the first bracket, and then combine and simplify. The only rule must remember is that I squared is -1. This is from the definition. The definition of I is that I is the square root of -1. This is the only rule you need to remember for you to be able to multiply two complex numbers. Okay? Now, I want to give you guys an exercise that you will do after, before we look at division. Maybe I should write it here. Are you able to see when I write over here?
Yeah.
Good.
No.
So go and multiply alpha plus gamma I multiplied by beta minus theta I. This is not 0, this is theta, it's a Greek symbol. Go and multiply this complex number at home. You tell me what you get.
It's alpha plus.
Alpha plus gamma. Gamma.
How is it written?
Gamma is written like this. In the Greek, that is just gamma. Have you heard of gamma rays? So this is capital gamma. The small gamma is that. This is small alpha. Capital alpha is just A. This is beta. The small beta, capital beta is just B. This is theta. Capital theta is something like that. Okay. Now, before we look at division of complex numbers, so you saw that addition and subtraction were very straightforward. Take real parts, imaginary parts, subtract them or add them, and then combine the results. And multiplication of complex numbers, you need to master how to expand a factored form of an expression, always remembering that the square root of -1 is represented by the symbol I. Now, for division, we need to learn two concepts, which I'm going to give you here. So the first we need to learn, and that's the reason I kept this example, because I said it's special. The first concept we need to learn for us to be able to do division of complex numbers is what we call complex conjugate. Complex conjugate. Ever heard of the term conjugate anywhere?
Radical.
Yes, good. We did radical conjugates when we were multiplying radicals, when we were dealing with exponents. And what does a radical conjugate do? It makes an irrational number rational. If you multiply a number by its radical conjugate, you get a rational number. You do away with the suts. The same way, a complex conjugate will multiply a complex number and do away with the imaginary part. It will give you a real number. So definition, given a complex number z as a plus ib or bi, then the complex conjugates of z denoted as z bar or z star. So depending on whichever book you read, all these two are correct. We could write z with a dash over it, or z raised to this asterisk, or z star. So if you have z as a plus ib, then the complex conjugate z bar is given by a by I b. You just change the sign of the imaginary part. So given any complex number, to find the complex conjugate, simply change the sign of the imaginary part. Okay? So example. What is the complex conjugate of the number 1 plus I? Let's have a table. Let's have a table of z bar, 1 plus I also want 2 minus 6i. I also want 0, maybe 1. So you guys give me the complex conjugate of 1 plus I. I've given you the rule. Simply change the sign of the imaginary part. So if you had a plus ib, complex conjugate is a minus ib.
1 minus I.
Good. So this is going to be 1 minus I. Why 1 minus I? Because the complex, the imaginary part of this is positive 1. So we change the sign of positive 1 to minus 1. Therefore, we have 1 minus I. How about 2 minus 6i? What's the complex conjugate?
2 plus
6i.
Good. 2 plus 6i. How about 0?
0.
0.
Reason?
There is
Why?
no imaginary part.
Why would you say 0?
The imaginary part
imaginary
and
part.
the real number.
Yeah, because
is
minus 0 plus 0 is still 0.
Good. So the imaginary part of this guy is 0. So when you take change the sign 0 minus 0, you still get a 0. How about 1?
1.
Negative.
1?
Same thing.
It's still 1.
1.
Still 1. Okay. In general, the complex conjugate of a real number is simply that number itself. So remember,
Excuse me, sir.
you could write complex.
Excuse me, sir.
Just a moment, let me explain something. When b is 0, you would write z as a. So it means the imaginary part is 0. So whether you change or maintain the sign of the imaginary part, the number will still remain. So if you have a real number, the complex conjugate of a real number is just the real number itself. Go ahead with your question.
What did you say the last one was? The conjugate of the last one.
1.
So it remains as 1.
Yes, 1 is 1. Actually, in general, any real number, the complex conjugate of any real number is the real number itself. And I'll try to explain that. When this b is 0, you just have z is a. So whether you change the sign of the imaginary part, because it's like you're having a plus 0i. So whether you write this as a minus 0i, it is still a, because 0 times anything is just 0. It doesn't change this real part. So in general, you can write this as a note somewhere if you like. Complex conjugate of a real number is the real number itself. Okay. And I told you that just like a radical conjugate rationalizes an expression, complex conjugate also makes a complex number real. For example, we have seen, sorry? Someone ask a question? Okay, we have seen 1 plus I. Complex conjugate of 1 plus I is 1 minus I. So when you multiply 1 plus I with 1 minus I, we get 2, which is a real number. You notice that the imaginary part has disappeared. Okay? Hello?
Yes.
Yes.
Can
You.
And then we need another concept, which is called absolute value. So now I can wrap this. So everyone knows how to find the complex conjugate. Simply change the sign of the imaginary part. So you must be able to identify which is the real part, which is the imaginary part. If you want complex conjugate, change the sign of the imaginary part. You have a complex conjugate. The next concept we need is absolute value. What's the absolute value of a complex number? Definition. Some people will refer to this as modulus. Modulus of absolute value of a complex number. Z is A plus IB, denoted by, some people write this as mod Z or Z under 2 bars, but I want you guys to be very careful with this mod Z, because in abstract algebra, this, when you write mod, it has a different mathematical meaning as opposed to what we mean by absolute value. So I prefer if we use this denotation, this to denote complex, the absolute value of a complex number Z, because mod means something else in abstract algebra. And it is given by A squared plus B squared. And now that we've done the complex conjugate, I can write, first of all, that definition is okay. But then I can also write that, no, then you take the square root. You take A squared plus B squared and then take the square root. So absolute value of a complex number given A plus IB, or the modulus is simply take the real part, square it, take imaginary part, square it, and then find the square root. Okay? So let me give an example before I talk about properties of this. So for example, let's have Z, then the absolute value. We will have a table, 1 plus I, 1 minus I, 1, maybe 2 plus 3I. So let's see. The definition is that the absolute value of a complex number is the square root of the sum of the squares of the real and imaginary parts. Good. So we have a complex number 1 plus I. What will be the absolute value? Using this definition. Sorry?
1 square plus 1 square.
What is that? Give me the final.
Square root of 1 squared.
Is 1 plus
1.
0.
2.
0.
2.
Square root of 2.
Square root of 2. Good.
Yeah.
It's square root of 2. Because by definition, it should be square root of 1 square plus 1 square, where 1 is the real part, 1 is the imaginary part. 1 square is 1, 1 square is 1, so 1 plus 1 is 2. So get square root of 2. How about 1 minus I?
So please repeat, I haven't understood.
Sorry?
Please repeat.
The definition is absolute value of a complex number is the square root of the sum of the squares of the real and imaginary parts. So given a complex number, Z is A plus IB. To find the absolute value, Take the real part, which is A, find the square of A. Take the imaginary part, which is B, find the square of B. Add A squared to B squared, and then find the square root of your final result. So for example, if you're given 1 plus I, in this case, A is 1 and B is 1. So 1 squared is 1, B squared is 1. 1 plus 1 is 2. So the square root of the whole thing is square root of 2. Okay? Is that okay, Hussein?
How is the square root 2?
How is the square root 2?
Yeah.
We know 2 is a prime number, and therefore the square root of 2 is going to be an irrational number. Okay? So just leave it as square root of 2 like that.
Okay.
We do not have an exact, no one knows the exact square root of 2.
So I have another question.
Go ahead, your question.
So in absolute value, then you ignore the I.
Sorry?
For absolute value, ignore the I.
No, you don't include the I.
Ignore.
I. Just take the real part and take the imaginary part. Remember, the real part is a real number. Imaginary part is also a real number, only that it's a coefficient of I. When I take B squared, I'll get a real number. A squared is also a real number. So when I add these two, it's a real number, and I can get the square root of a real number. You're not taking the positive part. This absolute value is always positive. Okay?
I have a question.
Go
The
ahead.
first part, 1 plus I. Yeah, that is the first one.
This one?
Yeah.
Yes.
You said the absolute value root 2, square root of 2.
Yes.
How? I thought 1 squared plus I squared will be 0 because it's 1 minus 1.
I see your problem. Let me repeat something. I see your problem. When you have a complex number, Z is A plus IB. Someone is talking, and I don't know who is talking to, and they have not muted. The imaginary part of Z is B, not BI or IB. For the real part, I just take A. Imaginary part, I just take this B. Don't include the I. Imaginary part is just the coefficient of I, full stop. So we now know that the complex conjugate of this guy is A minus BI. We have defined what a complex conjugate is. I've said just change the sign of the imaginary part. So yes. In the same way, the real part of the complex conjugate of this will be A. How about the imaginary part of this complex conjugate?
Minus B.
Good, minus B. So there is no I, okay?
Yes.
So when you have Z is 1 plus I, the real part of this guy is 1. Imaginary part of this guy is also 1. That's why I'm taking 1 squared plus 1 squared gives me a 2, then I take the square root, so the absolute value of this guy is square root of 2. Is it clear?
Yes, thank you.
Good. Any more questions on finding absolute value? So let's go ahead. What is the absolute value of 1 minus I?
Square root of 2.
Good. And you will see the meaning of absolute value when we do representation of this complex. It actually has a meaning. It actually has a meaning on the value of the complex number. So how did you get square root of 2? Someone want to explain?
1 squared, square root of 1 squared plus minus 1 squared.
Good.
So it still gives you 1 plus 1.
Good. So this is 2 because it's 1 squared plus minus 1 squared, square root of 2. How about absolute value of 1?
Square root of 1.
Absolute value of 1 is just 1 because the imaginary part is 0. How about the last one? The last one? How about the last one?
Square root of 13.
Square root of?
-1. 13.
Square root of 13, huh?
Yes.
Square root of 13. So this you will relate by taking square root of 2 squared plus square root of, so 3 squared is 9, 2 squared is 4, 9 plus 4 is 13. So the answer here is square root of 13. Good. So now, if you check the class notes, there are some properties of absolute value. For example, like maybe I can just list them. You have Z1 and Z2. Absolute value of this is this M as the product. The absolute values. And you can generalize this to any M. We also have that if you're taking absolute value, a quotient, although we have not done what's a quotient, so I'll show you later how to do a division. Provided that this guy is equal to 0. We also have that absolute value or sum is bounded above by sum of absolute values. Then lastly, we have that absolute value of a sum or a difference is bounded below by absolute value and difference in absolute values. You can take particular examples and prove these axioms. I don't want to take you through the pain of proving this, but there are mathematical arguments to prove this. Some of them have presented in the class notes. But if you want to prove this kind of things, for example, just take your Z1 to be 1 plus I, take Z2 to be 1 minus I. Then try to find absolute value of the product. So Z1 times Z2, we did somewhere it was, Z1 times Z2 was 2. So absolute value of Z2, Z1, Z2 will simply be 2. Then we have done absolute value of Z1 as 2. Absolute value of Z2 as square root of 2. So you realize that 2, which is absolute value of the product, is the same as square root of 2 times square root of 2. So this, it's okay. We have not done division, we had to do division, but you can also try this. You know how to add, right? We have done addition of complex numbers. What is Z1 plus Z2? When I add this to 1 plus I plus 1 minus I. Come on, guys. What is 1 plus I plus 1 minus I? How do you make complex numbers? We just did this.
Is 0.
0.
It's 2.
Two. So Z1 plus Z2 is 2. So what's the absolute value of 2?
2.
Good. Absolute value of 2 is 2. How about now the sum of the absolute values? So this is square root of 2 plus square root of 2. Is it true that 2 is less than square root of 2 plus square root of 2? That's true because square root of 2 plus square root of 2 is approximately 2.82 something. This is a number which is bigger than 2. So this is also true. Okay. And then, for example, for the sum, we have shown that Z1 plus Z2 is 2, and the absolute value is 2. But when you do absolute value of Z1 minus Z2, both of them are root 2. So root 2 minus 2 is 0, but this is positive, so 2 is always greater or equal to 0. So this is also satisfied. If there's someone who is interested in a rigorous mathematical argument proving this, I can always give that if you are interested. Okay, but we will not need this to do a multiplication. The only rule we will need is that when you take Z multiplied by its absolute, I mean its conjugate, you get the absolute value squared. Maybe let me give an example to show this. So for example, let Z be 1 plus I. Let Z bar automatically is 1 minus I. So if you multiply Z by Z bar, we have done this. This gave us 2. Okay? But we are saying this is simply absolute value of Z squared. In this case, Z is 1 plus I. So absolute value of Z is square root of 1 squared plus 1 squared, which is square root of 2. Which literally means that absolute value of Z, if you square this, is the same as square root of 2. The whole thing squared is equal to 2, which is what we have up here. So it means that this is true. Now, division of complex numbers. So we know what's the absolute value and we know what's the complex conjugate. To divide two complex numbers, find the complex conjugate of the denominator. Just as we were doing rationalization of denominator and numerator. Find complex conjugate of the denominator and then use this complex conjugate to multiply both the numerator and the denominator. So let me put that in writing. Division. Suppose we have Z1 is A plus IB, Z2 is C plus ID. This must not be 0, of course. Then Z1 divided by Z2. So we'll write this as A plus IB divided by C plus ID. The first rule, rule number 1, find complex conjugate. Complex conjugate of denominator. In this case, what's the complex conjugate of the denominator?
C minus ID.
Good. So the complex conjugate of this guy, you can write C plus ID. The complex conjugate is C minus ID. That is the first. Then the second rule, multiply both numerator and denominator. Denominator by this complex conjugate. By this complex conjugate. Conjugate. So what you have is that Z1 divided by Z2 is going to be A plus IB divided by C plus ID. Then we multiply the numerator by the complex conjugate. So the complex conjugate here is C minus ID. The same thing, C minus ID. Remember, this is like, it's like multiplying by 1. It does not change the meaning of this because this guy is cancelled out. Okay? So Z1 divided by Z2. We did multiplication of complex numbers. So you know how to multiply this. Huh? You know how to multiply what is in the numerator. Okay? I said just take elements of the first bracket, multiply everything by what is in the second bracket. Okay? But now the property I need to talk to you about, the last property, where we said that absolute value of Z squared is the same as Z multiplied by its complex conjugate. Notice that in the denominator, so what we will have in the numerator, after usual multiplication, you will have AC plus BD plus I into BC minus AD. So if you do what we did before in multiplication, take what is the first bracket, A times C plus A minus ID plus IB times C plus IB times ID. This is what you will get. We are dividing this by What I mean, I times I, so this should be, yes, this should be negative. Because I squared is, let me see, AC, then, oh, this is positive. Just a minute, so times t is negative, good, yeah, it's okay. This is positive because you have I times I, so I squared is negative 1, and this negative will give you a positive. Notice here that you have a complex number multiplied by its complex conjugate. We have said that should give you absolute value of that number squared. So what's the absolute value of this number? C plus ID. We said it is the square root of squares, sum of squares of the real part and imaginary part. Real part is C, imaginary part is D, squared, D squared plus D squared, take square root, that gives you absolute value. But when you square absolute value, you do away with the square root symbol. So here you will have C squared plus D squared. And finally, you can separate this, so you have AC plus BD divided by C squared plus D squared plus BC minus AD divided by C squared plus D squared. So for you to divide two complex numbers, you must know, number one, how to multiply two complex numbers. Number two, you must know the definition of the absolute value as square as the product of a number and its complex conjugate. That will help to simplify the numerator. So don't go around, trying to expand this. As long as you see a number multiplied by its complex conjugate, that is the absolute value squared. Just write the absolute value, take the square, and do away with the square root symbol.
Excuse me, sir.
Yes?
When we multiplied the A plus IB by C minus ID the first time we did it, the answer was AC minus BD and then plus I into bracket AD plus BC.
Yes.
And now this time we've changed the signs and the plus is where the minus is. Does it really affect the whole equation?
Not that it affects the whole equation. Remember here I'm multiplying two different things. So can I rub this? Can I rub this part?
Okay, yes.
Yes.
I need to see the difference. So first, we are multiplying A plus IB by C plus ID. And you've said correctly that this was AC minus BD plus I into
BD plus BC.
Plus BC, which is fine, okay? Is it okay?
Yes, that's okay.
Good. Now we are multiplying A plus IB by C minus ID. There's a different sign now.
All right.
So let me show you how you arrive at that. So you take A multiplied by C minus ID plus IB multiplied by C minus ID. Now A times C is AC. A times ID is minus AD I plus IB times C is BC I, okay, plus, then what do you have here? This is B times D, that's BD. Then you have also there's a negative. So there's BD, then I times I is I squared, okay? So we have AC minus ADI plus BCI, and then I squared is -1. So -1 times this negative part will make it positive. So you have plus BD, okay? Then now combine the real parts. So this is AC, this is BD. So you have AC plus BD. And then on the other side, I can factor out I so that I have BC minus AD. And that's what we have over here. Is it clear now?
Yes, it is.
Good. So shall we take an example?
Yes.
Have we done simultaneous equations?
No.
Simultaneous equations before? Hello?
Yes.
You've done simultaneous equations. Then I can show you another method. There's another method for division of complex numbers, but you need to have knowledge of simultaneous equations. You need to be able to solve equations that have more than one variable. I know in this class we have only done linear equations in one unknown. We will do linear equations in several variables. We do it in 20 variables or 30 variables or a million variables. But if there are those who know how to solve simultaneous equations, there's another method for dividing complex numbers, which is very easy. What else? Another example can I give?
Sorry, sir.
Yes.
Will you please show us the methods for the people who know how to solve simultaneous equations?
Okay, I will show you. Maybe one of these examples, one of these three examples, I will show you that method. Okay.
Okay.
Good. So first, let me see. Still have some 6 minutes. So the first one is very easy. What is the first step? Identify the complex conjugate. So we are doing this. Identify complex conjugate. What is the complex conjugate of the denominator?
Minus I.
Negative I.
Minus I. So then I take 1 plus I multiplied by minus I divided by I multiplied by minus I. What do we have in the numerator? So 1 times minus I is minus I minus I times I is I squared divided by, so this negative is the one that I put here. Okay. And then here I have negative I times I is I squared. Let's see what we have. So we have minus I as usual, then minus I squared is minus 1 divided by minus 1, because I squared is minus 1. So whether you are multiplying or dividing complex numbers, remember that I squared is negative 1. Don't leave I squared in your answers because it's negative 1. So this is going to be negative I plus 1 divided by negative 1 times 1, that's 1. So your final answer is 1 minus I. Okay. The second one.
Excuse me, sorry, sir. Just to confirm, the denominator after we've multiplied both the numerator and denominator with minus I rather, is the answer there minus 1 squared or minus I squared?
Where? Here.
Yes.
This is minus I squared, but I know I squared is minus 1. Huh?
Oh, right.
Yeah, so this is minus 1.
All right.
That's why minus 1 times minus 1 gives me a 1 in the denominator. And I can write this as 1 minus I. How about the second one? What's the denominator? 2 minus 3i. Identify the complex conjugate. What's the complex conjugate? Simply change this sign. 2 plus 3i divided by 2 minus 3i. Mean plus. So the sign here is negative. I change it to plus. Okay. Hello, are we together?
Yes.
Yes.
Am I going too fast? So we've done multiplication. So we know the real part. I will take 3 times 2 multiplied by negative 4 times 12. So that is 6 minus 12. That gives you minus 6 plus imaginary part would be 4 times 3. 4 times 2 added to 3 times 3. So that's 9 plus 6, 9 plus 8, that's 17. I. All this divided by, I know this is a number by its complex conjugate, take absolute value square. 2 squared is 4, 3 squared is 9, so this has to be 13. We have 6 over 13 plus 17I over 13. And then lastly, you have this is very simple, okay? Anyone have a problem on dividing this part C? Anyone have a problem for part C? Everybody is quiet. Did I lose you guys? Are you still there?
Yes.
Yeah.
Are you guys still there?
Yes,
Yeah.
we are here.
No.
Someone said no. What's the problem? Make sure you're not lost. Make sure we find you before you are off the road. You should go together as a team. Okay.
Teacher, kindly repeat part B.
Part B.
Yeah.
You know how to get complex conjugate?
Yeah.
So complex conjugate of 2 minus 3i.
2 plus 3i.
Good. And then we use this to multiply the numerator and to multiply the denominator. Okay? So the numerator, to get the real part, the part that doesn't involve I will take 3 times 2, and then I take, that gives me a 6, okay? So the numerator, 3 times 2 is 6, okay? Hello? Talk to me, guys.
Yes.
And
Yeah.
then
Hello.
4 times 3 is 12, okay?
Yes.
But there's an I times an I, so that's a negative, so this is negative 12. So 6 minus 12, that is what gave me negative 6 as the real part. Okay?
Yes. Yes.
And then the imaginary part, I take 4 times 2, that's 8i, and then 3 times 3. So 4 times 2 and 3 times 3. So 8 plus 9 is 17. I'm done with the numerator. Then the denominator, I realize that I'm taking a number multiplied by its complex conjugate. And there is this rule we wrote somewhere that a number multiplied by its complex conjugate is z squared. So save yourself unnecessary long computations by remembering this rule. So absolute value of any of these guys is simply 2 squared plus 3 squared, then I take the square root. But if I square this, I simply get 13 as 4 plus.
Yeah. 13, very good.
It's just 3 plus 4i multiplied by 2 plus 3i. The numerator. So then you take 3 into 2 plus 3i plus 4i into 2 plus I. 3 times 2 is 6. 3 times 3 is 9i. 4 times 2 is 8i. And then lastly, plus 4 times 3 is 12. And then I squared. So you know this gives you 6 plus 9 plus 8 is 17i. I squared is negative, so there I have minus 12. Therefore, combining, I have 6 minus 12 plus 17i. So this gives me minus 6 plus 17i. That is what I have up here in the numerator.
So the other method.
Sorry? The other method? Yeah, okay.
The other method.
Okay, let's do the other method. But
Before you go to the other method, can you leave the answer at that place where you negative 6 plus 17i over 13?
You must do what?
Separating.
Do the denominator.
No, I'm saying, can you leave the answer at negative 6 plus 17i over 13?
Yeah, you can leave your answers like that. It's okay.
Oh, okay.
Wait, so how come you didn't leave the 13 in a square root?
This is the rule I'm using. if you multiply a number by its complex conjugate, its absolute value squared. So it is this square that removes the square root, okay? This square removes the square root from the absolute value. So absolute value of this number is root 13. But when I square it, I do away with the square root. That's why I don't have a square root in this 13. Okay?
Yes.
For those who have done simultaneous equations, let me show you the other method using this example.
So it's time.
It's time.
You just wait.
It won't take long. It won't take long. Huh? Give me some, maybe 3 minutes. So you have 1 plus I divided by I. Okay. We want to divide two complex numbers. We know that the answer is going to be a complex number. Okay. Because a complex number is a field. I will give you some axioms that shows you a complex number is a field. Because so that means if you divide the two complex numbers, you must always get a complex number. So let this be some other number a plus ib. We know it must be a complex number. Okay. Now, what do? Multiply both sides by I to do away with this fraction. So 1 plus I is going to be a plus ib multiplied by I. Open the bracket on this end. So 1 plus I is going to be, this is a times I plus I times I is I squared. Okay, so that's -1 times b. So this is minus b. Two complex numbers will only be equal if the real part is equal to the real part and the imaginary parts are also equal. So if I give you two complex numbers, a plus ib and c plus id, then these two numbers will be the same if a is c, a is c and b is d. So in this case, I have 1 plus I is equal to -b plus ai. So the real part of this part is 1. The real part of this side is minus b. So that means minus b is 1. Therefore, b is going to be -1. And a, this is 1, coefficient of this guy is 1, coefficient of this guy is a. So it means a is 1. So when you have a is 1 and b is -1, here you have 1 minus I.
1.
Which is what we have here. Does it make sense?
Yes.
I extracted two simultaneous equations, one in B and one in A, and I get the solutions for A and B, and gives me the answer 1 minus I. It can also work for this, it can also work for this. Now the last thing I wanted to show you is powers of I. So as an example, I power 27. This is the last thing. You're asked to find I power 27. We did rules of exponents. This is the same as I power 26 plus 1, because 27 is the same as 26 plus 1. You remember the rule A times n multiplied by A to the m is the same as A to the m plus n. So what I've done is to decompose this 27 as 26 plus 1. And remember, this is the same as I to the 26 times I to the 1. But I to the 26 is the same as I squared 12 times I. I'm using the rule that A to the m raised to n is A to the m n. I squared is -1, so you have -1 raised to 12 I. When you take -1 raised to any even number is positive, so therefore this gives you I. So I to the 27 is going to be I. So as an exercise, go and find I to the 1999. Any question? We stop there. I know we are past time. I've consumed, wow, 7 minutes. Sorry about that.